everyone. So, quick reminder, your test should be open now, and you can take it today or tomorrow up through midnight. We are working on a new chapter, chapter 7. It's a pretty quick chapter. It's more concept-based. We're not going to be doing a whole lot of math or anything with it. So hopefully we can get through all of it today. If not, we'll do a little bit on Tuesday of next week. All right. Sorry. All right, so chapter 7, looking at periodic properties of elements. So how we can look at the periodic chart and see these trends, or are there certain atoms that are similar to each other property-wise, and how does two neighboring atoms relate to each other size-wise, how they like electrons, things like that. So here is a periodic chart, and this is the ordering that they were sort of discovered in. So some of these more common metals, carbon and sulfur, were actually identified earlier, and then they filled in. So it's not like, because hydrogen's the lightest one, we discovered that first and we added from there. We sort of found a bunch of them in the 17 and 1800s. And the later ones we kind of filled in after the fact. Mendeleev, Dmitry Mendeleev, who's sort of given most of the credit for the organization of the periodic chart and discovery of the periodic chart, was able to, kind of put this thing together, group things that had similar properties, right? So all the alkali metals in that first column behave in a similar way. Everything in the noble gases behaves sort of in a similar way. And, but some of these weren't discovered yet. And he was actually able to predict some of these, specifically germanium. He knew about silicon and he knew about carbon, and he kind of guessed that, oh, there should be something else that would have this mass and have these sorts of properties. And he was actually they were able to discover it after he had predicted it. He had said, there should be something that, has an atomic weight of about 72, and it's got sort of this kind of density. And he was able to make all these predictions about it. And then they were able to confirm it. So Mendeleev's table was based on atomic masses. It was one of the most fundamental properties of elements that we knew at the time. So atomic mass being how heavy the atom is. That's including protons and neutrons. We don't include the electrons. About 35 years later is when Rutherford discovered the nucleus. And we had that nuclear atom idea where we've got protons, neutrons, and then they started organizing the periodic chart. So mostly later on actually organized it by the number of protons, because he found that the number of protons was what gave an element its elemental properties, right? I can change neutrons, I can change electrons. If I change protons, it becomes a different element altogether. So when looking at our periodic chart, we have these things called periodicity, or this repetitive pattern of properties for elements based off of their atomic number. So if we line them up in a row from smallest atomic number to largest atomic number, which is in fact the way the periodic chart is organized, we will see that there are trends for the following properties. So one of them is the size of the atom and also its ions. Ionization energy. So ionization energy is the amount of energy it takes to pull an electron away from the atom. There is a trend to that. Electron affinity. So how much does something kind of love electrons? That's also something we can read off the periodic chart, or at least I could look at, two neighboring atoms, aluminum and boron, and be able to figure out which one would like to have the electrons more. And then groups with their chemical properties. Well, this last part here, we're not going to go into a huge amount of detail, but know the things in column 1 have similar properties, right? The alkali metals, the things in column 2, the alkaline earth metals will also have similar properties, so on and so on. So in order to explain some of these trends, the size, ionization, and things like that, we need to talk about this thing called effective nuclear charge. All right. Effective nuclear charge is sort of like how strong is the nucleus acting on the surrounding electrons. So many properties are going to depend on this effective nuclear charge. And this is sort of the attraction between the nucleus and really the valence electron. So the electrons in that outermost shell. All right, so this nucleus has an overall positive charge, right? And that positive charge is going to pull on your valence electrons. How much it pulls is classified with its effective nuclear charge. Now, electrons are going to be attracted to the nucleus, but there are two things that are playing into that. One of them is the number of protons, okay? So if we have a lot of protons, this becomes very attractive for the electrons. But we also have the force of other electrons repelling or pushing back against those valence electrons. So if I've got, let's say I've got a layer, another inner layer of electrons here, those are going to have what's called a shielding effect, where they're going to kind of keep the nucleus positive charge away from those valence electrons. So those two forces are important in calculating our effective nuclear charge. So there's a pretty simple equation, and it's this ZF, which is your effective nuclear charge. So how strong is your positive nuclear charge? And it's going to equal your atomic number, which is the number of protons, minus your what's called your screening constant. And usually your screening constant is close to, if not almost the same as your inner electrons. So how many core electrons do you have? So let's look at one example or two examples here to kind of explain this. So I have, we're going to look at lithium and beryllium. So lithium and beryllium, find them on the periodic chart. You can see that they're neighbors to each other. Lithium, inside its nucleus, it has, depending on what isotope you're looking at, it'll have, lithium will have 3 protons, and it could have, in some instances, it looks like it'll have 3 neutrons. Sometimes it has 4 neutrons. But the neutrons, the protons are what are important with this effective nuclear charge. The neutrons don't have a charge, right? They're neutral, so they're just sort of like, almost like dead weight. They're just hanging around in the nucleus. So I'm going to put a little 3+ here, or 3p+, something to let me know that I've got 3 protons in my lithium nucleus. Now over here at beryllium, how many protons do I have? In order to be beryllium, I have 4 protons. Okay. So if you think about this like a magnet, this has a magnitude of 3 for its magnet. This has a magnitude of 4 for its positive magnet. So this is like a stronger magnet, okay? So this has more like positive pull on those electrons. So let's add some electrons. So if we're at the 3p, or I mean, if we're at lithium, the electron configuration, this is 1s2, 2s1. This electron configuration is 1s2, 2s2. So both of them have 2 electrons in this 1s orbital. So I'm going to put a little electron there, a little electron there. Same thing with this one. Okay, we've got an electron here, an electron here. These are the core electrons or the inner electrons. Now around that, I've got my 2s orbital, and there is an electron floating around there. Over here, instead of having one electron in this outer shell, I have 2 electrons. So let's play around with that Z F EF value. Okay, so the ZF is going to equal your Z, which is your number of protons, minus your screening electrons, or the electrons that are the core electrons. So how effective is this nucleus over here? Well, let me move this a little bit so we have slightly more room. So I've got 3 protons. And then how many core electrons do I have here? Well, the electrons that are kind of getting in the way, this one here and this one here, so it's 2. So the effective charge on this is a +1. Now let's compare that to beryllium. Beryllium has 4 protons. It has a stronger magnet. How many screening electrons does it have though? It only has 2. Yes, it does have an additional electron out here, but that's in the outer onion layer. That isn't getting in the way of the electrons' access to the nucleus, okay? So this 4 only has to break through these 2 inner electrons. So what happens here with our effective nuclear charge is we actually have a +2. So the effective nuclear charge here is stronger for beryllium than it is for lithium. And this is a trend that we see when looking across the periodic chart. As you move from left to right on the periodic chart, your effective nuclear charge, or your ZF, is going to increase. Because you're increasing the number of protons, but you're not increasing the number of inner core electrons that you have. So I'm gonna pull back up here. So we've got our effective nuclear charge. ZF is that Z minus S. So the effective nuclear charge, it increases as you go across a period. Now this is a little bit counterintuitive. It doesn't matter a whole lot, but as you go down in a group, your effective nuclear charge increases slightly. It pretty much stays the same, okay? So if I'm looking at sodium and lithium, sodium may have a slightly larger effective nuclear charge. And you may be thinking, well, why would it have a larger as you go down? Because when you get more electrons in the core, they kind of interfere with each other and they inhibit its screening ability. So the more electrons you have as core electrons, actually the less effective they are at blocking the nucleus, which kind of sounds counterintuitive. But don't worry too much about this one. This is really what I want you to think about, okay? As you move from left to right, you are going to have a larger effective nuclear charge. So I want you to look at silicon and sulfur on your periodic chart. Which one would you expect to have a larger effective nuclear charge? So if we're looking at silicon and sulfur, sulfur is farther to the right. So we're going to say sulfur is going to have a larger effective nuclear charge. Sulfur has 2 extra protons. So its magnet is got 2 extra positives in it. It's going to pull those electrons harder, or it's got a stronger force. So this effective nuclear charge has an effect on quite a bunch of different things within the atom, but one of them is the size. So when we're talking about the size of an atom, hold on one second. When we're talking about the size of an atom, it would be the distance between, it's pretty much the distance between the nucleus, the center of the nucleus, and the outermost valence electron if it was bonded to another atom. Okay, so we're not classifying it as the atom is free alone by itself, but it's actually been sort of pushed up against another atom. When it gets to the place where it doesn't want to get any closer to the other atom because there's a repulsion between electron groups, that's what we call our radius. So it's the distance from here halfway to there, the full distance from nuclei to nuclei. is D. We're 1/2 of that to get our bonding radius. So how does that radius, how do we find that periodicity, or what is that periodicity on the periodic chart? How does it get bigger? How does it get smaller in reference to our periodic chart? So looking at here, sizes of atoms. So in general, your bonding atomic radius, so the radius, as the radius gets bigger, we are going to have a bigger atom. As it gets smaller, we're going to have a smaller atom. So the atomic radius, or the size of the atom, is going to decrease as you go from left to right. So if you want to, over by helium, you can write in the upper right-hand corner, smallest. Why do these atoms decrease in size as we move across the periodic chart? So lithium is going to be bigger than beryllium. Beryllium is going to be bigger than boron. What's happening is our ZF, or our nuclear charge, increases as we move from left to right. So if the nucleus has a stronger pull, the atom itself is going to be smaller. Or that nucleus, that magnet that we have in the center, is a bigger magnet as we move across. So it's going to pull on that outer onion layer. Now, we are going to increase in size as we move down. All right, so rubidium is going to be bigger than potassium. Potassium's bigger than sodium. Or if you want, in the lower left-hand corner of your periodic chart, where 87 FR is, you can call that Fat Frankie. Okay, so he's the biggest atom, lower left-hand. Now, I said effective nuclear charge increases slightly as we move down. It's super small, the increase. So what's really happening, why these are getting bigger? It's getting bigger because our outer onion layer is increasing, right? Every time we go down a step, we are increasing our electron outer shell, right? Hydrogen, so I can get out of this. So if we do hydrogen, hydrogen has 1 proton in the center, and it's got 1 electron in, this is the 1s, and we've got 1 electron here, okay? This is hydrogen. If we look at lithium, which is 1 step down, or 1 spot down, we've got 3 protons. We have this 1s orbital, we'll have 2 electrons in it. All right, so we got an electron there, and we got an electron there. And then we've started to actually fill in our second onion layer. So here, we've got an electron in the 2s. So this is just filling in that first layer. Lithium is filling in now, the first is filled, and now we're filling in the second as well. If we go to sodium, I would have to put a 3rd layer around it. So we're just getting bigger as we go down. It's kind of like we're nestling the Russian dolls. So this has 1 Russian doll. We've clipped the bigger Russian doll around the smaller one, so on and so on.
Can you go over again how ZF is determined? It's the number of protons in the nucleus, and then it's the number of electrons in which shell?
It's the number of electrons that are sort of your core electrons, or in the center. So for this one.
So like every ring exclusive of the valence electrons?
Exactly. Mm-hmm. So for this one, we have 3 protons, right? So we take 3 minus the 2, and this would give me a value of 1. This here, well, it's 1 proton and 1 electron. That hydrogen doesn't really follow suit. So if we were to do, let's say we were to do nitrogen. So nitrogen is in the same column as lithium. Move this out of the way. Okay, so drop that down here. So this has a plus 1. Nitrogen, its center bar magnet is what, 7? Because we have 7 protons. I'm gonna put a 7 plus there. It does have the 1s inner onion layer, right? So this is the 1s, or the first energy. So we'll even just do it as 1. It's got an electron there, an electron there. Now we're starting to fill the second energy, so n equals 2, and it has 1, 2, 3, 4. So there are 4 electrons in this sort of sp thing going on. Those 4 electrons are not included. We would only look at the level that's at 1. So the electron configuration for this is 1s2, 2s2, 2p2. We would ignore the 2s and just look at the 1 for the screening electrons. So here we have 7 as our atomic number minus just those 2 electrons is going to give me a positive 5. So this pulls much more than lithium. Does that make sense, Brittany, where those numbers came from?
The numbers, yes, but why wouldn't you include the 2s2?
This one here? Because
Yes.
this is both at the same floor. So yes, it's in a different orbital, but they have the same energy.
Oh, so it's not, so it's on the floor level that we're looking
Exactly.
at.
Yeah, so go down to the lowest number. If this was complete, like if we were to fill this in completely and do the guy underneath it, like phosphorus, then we could count the other ones as screening electrons. But if this is half filled, we're considering those valence electrons. And think about what column is nitrogen in. Nitrogen is in column 1, 2, 3, 4, so it has 4 valence electrons. So all those are unpaired outer electrons. So we just use the 2 in the center. And this should be a 3. I don't know why I put a 2. This should be a 3. Let's add 1 more electron in there. I was looking at carbon. Yeah, let's make this a 3. So yeah, we don't look at the outer guys, just the inner guy. Any other questions on that ZF equals Z, which is really just protons, minus S, which is any of your inner electrons? And this number isn't perfect, okay? The screening electrons, that number isn't 100% perfect, but it'll give you a general idea trend-wise. So size-wise, lower left-hand corner, biggest atoms, upper right-hand corner, smallest. Determining the size of ions. So kind of separate these two. I'm going to put a line right here just so that we can see. All right, so underneath on the bottom of each of these, this is the size of the uncharged particle. So this follows the trends that we know of as far as, we get smaller as we move to the right. Why is the atom getting smaller? Because there's more protons. It has a higher effective nuclear charge, so it's pulling the outer electron in closer. It gets bigger as we move down because we are adding, every time we go down, we add an onion layer. Now, when we are looking at the size of an ion, it will depend on a couple different things. It depends on the nuclear charge. It depends on the number of electrons. And it also depends on the orbitals in which the electrons reside. So here's my lithium, traditionally its size. When it becomes a positive, or if we lose an electron, the new ion will have a smaller size. Now, why is it smaller? Well, we got rid of an electron, so we got rid of like the outer onion layer. And after getting rid of the outer onion layer, that also helps the nucleus to pull a little bit harder on the remaining electrons. So it kind of hugs everything in. So when we go from a ground state atom to a cation, we will get smaller in size. Right? That's true for all of these. So anything that loses electrons is going to get smaller in size. Sodium here, smaller when it's the sodium cation. Same thing if we are going to drop 2 or 3 electrons. Now the opposite is true if we're gaining electrons. So over here, fluorine is actually a pretty teeny tiny atom. But when we add an electron, we are going to increase its size. So we're filling out the outer onion layer. In just a second, I want to make sure that there isn't anything else that I want to say specifically about that before we do some practice. Really, that's it. So yeah, for cation, so if you want to, right, let me clear this out. If you want to write this down somewhere, cations are always going to be smaller than the parent atom, right? Or your metal cation, the metals are going to form smaller atoms when they charge. Anions, or all the non-metal things towards the right side of the periodic chart, they are going to get much bigger. The smaller cation is happening because we're losing an electron, we're losing an onion layer, and we are increasing the amount of nuclear charge, and we're also decreasing repulsion between electrons. Anions, we're adding electrons, we're increasing that outer onion layer, and we're also, electrons want to repulse each other. They want to get away from each other, so they kind of spread out. So you can almost think about what's happening with the anion, like fluorine. Traditionally, fluorine has 7 electrons in its outer shell. So think about 7 friends holding hands in a circle, okay? If we now add an electron or we add a friend to that circle, and you have 8 friends in the circle, what do you have to do for you all to hold hands? You all have to step back a little bit to make a little more room for that 8th person. So we can look at the size of ions and create what's known as an isoelectronic series. And isoelectronic means that they have the same electron configuration, so same number of electrons. A series means that we have a different number of protons, same number of electrons, and same structure as far as where the electrons are distributed. But their size will change because the protons have changed. So let's look at oxygen when it's charged. Okay, so oxygen 2-, fluorine 1-, sodium 1+, magnesium 2+, and aluminum 3+. All of these things have a different number of protons. So oxygen has 8 protons, fluorine has 9. You can look on your periodic chart. All these 2 things are hugging neon. They're sitting right before neon. These 3 are come right after neon. And all of them have 10 electrons, which is isoelectronic to neon. So these all have the electron configuration of neon. But the thing that's different, they don't have the same number of protons. Who has the most protons here? Aluminum over here has the most protons. So you can think of aluminum as having the strongest magnet in the center of it, or the biggest nuclear charge, biggest pull. So if this has a really strong charge or a strong pull from the nucleus, it's going to take those 10 electrons and it's going to hold them really, really close. So aluminum is actually going to have the smallest radius. Even though it has more protons, the protons are going to pull on those 10 electrons for dear life. As we go down in the number of protons here, our effective nuclear charge also goes down. This is a weaker magnet. This is a really weak magnet. So this can't hold on to the electrons, even though it still has 10 electrons. It can't hold on to those 10 electrons as well as aluminum does. So it's smaller, or rather it's larger in size. Smaller nuclear charge, larger radius. So decreasing ionic radius or smaller atom. Here we are decreasing nuclear charge, but we're increasing the ionic radius. So let me give you a set of isoelectronic ions, and I want you to put them in order of size. If I can get out of here. I'm gonna give you all Ga3+, chlorine minus, argon, sulfur 2 minus, calcium plus, and, or sorry, potassium plus, and calcium 2 plus. So the first thing I want you to do is order by effective nuclear charge. So which has the strongest nuclear charge, which has the weakest, and then order by size. And do both of these small to large. And this one too, small to large. You might want to, for each of these, say how many protons and how many electrons you have for each one. That may help you to order out effective nuclear charge and size. I'll give you another 2 minutes. So in this situation, these are all, well, except for argon. Argon isn't an ion. But they're all isoelectronic to each other, meaning they all have the same number of electrons. So I can just fill in right off the bat that we have 18 electrons for each of these. What is going to change here is the number of protons. So gallium over here has 31. Then we have calcium that has 20. Potassium has 19. Sulfur has 16. Argon has 18. And chlorine has 17. So how strong are these protons going to be acting on those electrons? Well, the least effective magnet, where did the 18 come from? So yeah, I guess for 20. So I guess for gallium, it wouldn't be 18 because we have those core electrons. Let's ditch gallium then. Let's ditch gallium. We won't work with gallium. I mean, it's ideally the same thing because the transition metals are core electrons, so we almost just don't even include those as having any sort of effect on the electron configuration. But we'll just ignore gallium. We'll work with these guys. So outside of that one, so we've got our 17 magnet, we've got our 18 magnet, we've got our 16 magnet, 19 magnet, and 20 magnet. So the weakest magnet here is going to be the 16. So for 1, I'm going to put sulfur 2- as my weakest magnet, or has the least effective nuclear charge. The next thing will be chlorine, which has got 17. Okay, so chlorine is got a little bit stronger of a nuclear charge. And then we just continue down the path from there. So then we've got argon. And then we have 18, 19, then we've got potassium. And then calcium. All right, now the opposite is going to be true for the size, because as you become better at pulling your electrons in, or your magnet is stronger, you will get smaller in size. So hopefully you guys put the opposite ordering for size here. So I'm going to put calcium as the smallest of these atoms because it's pulling the electrons so hard with all of those protons. Then we're going to go for potassium, then argon, then chlorine charged, and then sulfur charged. So these two things, effective nuclear charge and size, will be sort of inversely related to each other.
Is it just as effective to look at the charge of the atom and kind of order them? Because you can look at, you can see that it's ascending.
As far as charge is concerned?
Yeah.
Yes, except like if I was to give you something like a calcium 2+ and magnesium 2+, they both have the same charge. Which one would be the bigger atom? In that case, we're going to say that calcium is the bigger atom. If you look at your periodic chart, calcium sits below magnesium, so it's going to be bigger, and its cation will also be bigger. Okay, so just make sure if you are going to do that, that they are all isoelectronic to each other, putting them in order. All right. If I ask you about two separate ions that aren't isoelectronic to each other, look at the periodic chart. All right, so Next thing that we can talk about trend-wise is this thing called ionization energy. So ionization energy is the minimum energy required to remove an electron from its ground state. And it's specifically the material in a gaseous form. So the first ionization energy is going to be the energy required to remove the first electron. The second ionization energy is going to be the energy required to remove the second electron. The third ionization energy to remove the third electron. Now, put down somewhere in your notes that the first ionization energy is always going to be the smallest. So the ionization energy of 1 is smaller than the ionization energy of 2, smaller than the ionization energy of 3. So what that means is it's easiest to remove the first electron. It gets more challenging as you remove the second and the third. So for instance, for aluminum, aluminum likes to form a 3+ charge, right? Removing that first electron is easy. Removing the second electron requires a little more energy. Removing the third requires more than either the first or the second. Why is that the case? Because as we remove electrons, the nuclear charge gets stronger, it gets more efficient. So all the electrons pull in a little closer. So it's going to be harder to pull that electron away. And so specifically ionization energy 1, for aluminum, the ionization energy of 1 is going to be equivalent to going from aluminum to aluminum with a plus charge, and we've removed an electron, okay? The second energy is going from aluminum with a plus charge to aluminum with a 2+ charge. And then the third one right over here, energy of this is supposed to be the second one, of the third one is going to be going from the aluminum with the 2+ to aluminum with the 3+. So removing the 3 electrons, it may appear like it's simultaneous, but it's not simultaneously happening. We're going in stages. So here is a chart that shows us the ionization energy of a couple different elements. So sodium, magnesium, aluminum, silicon, so on and so on. So sodium likes to form a +1 charge. So in the amount of energy it takes to remove that first electron is about 496, and this is in joules, I believe. Oh no, this is in kilojoules per mole. So this is the amount of kilojoules in 1 mole of sodium to remove that first electron. Now, does sodium like to lose 2 electrons? Think about where it is on the periodic chart. If sodium loses 1 electron, it becomes like neon. Would it want to lose a second electron? No, then we're making the configuration unstable again. We're like tearing an electron from a complete outer shell. So you'll see this zigzag line here. This represents a separation between valence or outer electrons and then inner shell electrons. So doesn't require a whole lot of energy to remove that first electron from sodium, but to remove the second electron, I would have to start to delve into inner shell electrons, and that's not going to happen. So it takes a buttload of energy to remove one of those inner electrons. They're in a complete set, they're closer to the nucleus, they're happy. So this doesn't really happen. Okay? Magnesium, which likes to form a 2+ charge, the first electron requires a reasonable amount of energy, not a whole bunch. The second electron to remove does take more energy than the first, right? We did say that the second ionization energy is more than the first ionization energy, but look what happens if we try to go into a third ionization energy. It skyrockets again into like 7,000. Why is this happening? Well, look at where magnesium is on the periodic chart. If we lose one electron, we become sodium's configuration. If we remove another electron, we become argons, or rather neons. If we remove one more, we're now removing inner shell electrons. This is true as we move down the chart, okay? Aluminum, again, likes to lose 3 electrons. First one, second, third. If we tried to remove that fourth, a lot of electron, or a lot of energy to remove that core electron. And so you can even make a note here that this is aluminum with a plus charge. This is aluminum with a 2+ charge. And this is aluminum with a 3+ charge, right? More energy as we sequentially go down. So as far as how ionization energy relates to the periodic chart, if I was to give you like 2 adjacent atoms and I said which one has a higher ionization first, specifically first ionization energy, in general, ionization energy increases across a period and it will decrease down a group. So hopefully you have your sizes in the corners. That's what I do. I just remember like the corners of my periodic chart. There we go, great. Okay, so we know that these are the smallest, these are the biggest atoms. The opposite is true for ionization energy. So the ionization energy in the upper right-hand corner, it's going to be the largest. It's going to be the smallest over here. So look at, for instance, we can look at helium. Okay, helium's first ionization energy is 2,372. Does helium want to give an electron up? No. It takes a lot of energy to get rid of that electron. So it's probably just not going to happen. It's got a complete set. It's happy. Same thing with fluorine. It's not quite as high as helium's, but fluorine, you know, to remove that first electron from fluorine, you would need 1,681 kilojoules per mole. It's a lot of energy. It's going to end up just probably just grabbing an electron. Now go over here to cesium in the lower left-hand corner. It has an ionization energy of 376. So it does require a little bit of energy to remove that electron, but nowhere near as much as any of these. And it's still gonna, you know, eventually it's gonna wanna give that electron up. These guys like to give electrons. These guys like to take electrons. It's much easier to give the electron here, doesn't require as much energy. There is one irregularity to the ionization energy. If you notice here, nitrogen is a little bit higher than the other ones. Okay, why is nitrogen a little bit higher than its surrounding neighbors? You would think that it should sort of follow the trend. Well, look at nitrogen here. It has this sort of balanced set. So in order to remove one of these electrons, you would have to like undo this nice sort of balanced spin. Every sort of orbital is filled with one pair. One exception there. All right, we can skip over that. Okay, so this is sort of the opposite of ionization energy, is this thing called electron affinity. Electron affinity is the change accompanying the addition of an electron to a gaseous atom. So if I have chlorine and I add an electron, I am going to become chlorine with a minus charge, and I'm actually going to release some energy. So chlorine with a negative charge has less energy than chlorine without the charge, or this is an exothermic reaction. For most of the elements out there, it is in fact an exothermic reaction. So for most of them, having absorbing an electron is going to make the system sort of more stable or slightly calmer. So how the trends go for electron affinity. The minus the noble gases, because the noble gases here actually have a positive charge, which means that if you try and stick an electron in there, it is going to be endothermic, or it will actually absorb energy. So we don't really put electrons in there, but starting with fluorine, electron affinity over here, it's going to release the most amount of energy when it eats an electron up, is fluorine. And it usually tends to stay the same within a column. These numbers sort of hover around each other, but your affinity for electrons are going to decrease as you move towards the left, right? Or your affinity will increase as you move towards the right. Now, why we've got this negative number, that negative number is saying that, you know, you're releasing 328 joules for every electron that you absorb. Why would an electron want to absorb, or why would an atom want to absorb an electron? It's because it's kind of like kids. They have a lot of energy, right? And they tend to do better. They're more stable when you release that energy. Same thing with atoms. The more energy that these atoms can release, the more stable they're going to become. So the more negative number here, the more likely it is to absorb an electron. If it's positive, again, it becomes more unstable. So we see that happening with the noble gases, and then also nitrogen. Nitrogen is a exception to the rule. But in general, these guys over here, right, in the lower left-hand corner have the lowest energy released, or the least desire for an electron. So they have the lowest electron affinity. These over here on the upper right, minus our noble gases, have the highest electron affinity. That kind of corresponds with, you know, what we've thought as far as who likes electrons and who doesn't like electrons. So this electron affinity chart is something that you may want to have access to when you are taking your next exam. Right? You can find it in your text. It's also in the guided notes as well, so on the last page. Last trend that I really want to go over on the periodic chart is metallic properties. So the most metal-like things, lower left-hand corner, so where fat Frankie is, those are very metallic-like things. Upper right-hand corner, least metallic. This follows that zigzag line that we had on our periodic chart. So all of these are metals. Most of the things on the periodic chart are in fact metals, right? The lanthanides that aren't inserted in there, we would consider those to be metals. Things that are non-metals, hydrogen, carbon, phosphorus, selenium, iodine, At, all of these over are nonmetals. And then we have a couple things, boron, silicon, germanium. These right along here are known as metalloids. They have properties that are like metals, but they also behave not like metals. So we call these things semiconductors, and those are pretty useful in electronics. Silicon, we call it Silicon Valley. We don't call it like Copper Valley. We call it Silicon Valley because they use silicon a lot in electronics. Metalloids, it's easy to turn on and off their conductivity, which you can use in computers. And some of the properties of metals, they tend to have more consistent properties. They have shiny lusters. They're good conductors of heat and electricity. They tend to be malleable, meaning we can like bend them, and ductile, we can stretch them into wire. Most of them are solid at room temperature, except for mercury, and they tend to have low ionization energies. Remember, low ionization energy means that they it doesn't require a lot of energy to take their electrons. They want to give up electrons. They like to form these cations. Non-metals have much more varying charges. So you can have them as solids, liquids, and gases at room temperature. If they are solid, they're usually dull and brittle. Here's a picture of sulfur. They have just, in general, just much more varying properties. Large negative electron affinity. When we say large negative electron affinity, it means they give up a lot of energy when they get an electron. So they gravitate towards electrons. They want to become more stable. So they tend to form anions. If if you were to order how metallic something is, going back to this chart here, iron is more metallic than copper. Okay. Cesium is more metallic than manganese. As you move towards this lower left-hand corner, you increase your metallic property. As you move towards the right, you decrease it. So aluminum has less metallic properties than, say, rubidium over here. Same thing as we move up and down. Potassium is less metallic than rubidium. Sodium is less metallic than potassium. So with a lot of these trends, it's just going to be sort of as simple as putting the right things in the right spots on the periodic chart and then knowing the trends, how they differ. There are a few more slides and a little bit more in the text on this stuff, but we are not going to get into metal and non-metal chemistry. So you can sort of skip over that. And that's it. That's it for that chapter. So not too bad of a chapter. We will leave it at that. Please make sure to take your test before tomorrow at midnight. If you're having any issues with that, let me know now. So if you need some sort of weird extension because you happen to have work or whatever, because I know we usually do it on Sunday, Monday, tell me now and I can make adjustments for you there. Otherwise, have a really good weekend. Early voting ends on Saturday, so make it happen. North Carolina is rocking it right now. I think we're at like 85% of the number of votes that were dropped off in 2016. So we have almost put more votes in than people voted in the last election. So, and we haven't even gotten to election day. So it's pretty awesome. If you need any help with that, let me know. Whose jersey am I wearing? I am wearing Hester from the Bears. I'm from Chicago, so I was into the Bears for a while. They haven't won the Super Bowl since I was born in '85. So my husband though is my husband went to Clemson and he's a Clemson fan, and it's much more fun being a Clemson fan than it is being a Bears fan. So if you're into college football, you know what I mean. Other than that, you guys enjoy your day. Good to see y'all. It's sunny outside, so go enjoy some of the sunny weather. Brittany? No?